So everything I'm going to talk about is joint work with Manny Acker and Manfred Einsiedler. Right, so what I'm going to talk about is an arithmetic application of the joinings classification by Einsiedler and Lindstrass. So specifically so the plan is to look at rational two-dimensional subspaces of R4, and to each such subspace we associate 4 complex multiplication points, and the theorem will essentially state that the subspace together with the tuple of these 4 complex multiplication points will be equidistributed, but it will be made precise in a minute. Okay? So everything we do here is pretty much in the spirit of previous works of my co-authors together with Uri Shapira. Okay, so I promised something more precise. So so for any two-dimensional subspace, I would call this a plane sometimes, so just be warned. We define the discriminant of the subspace like this. So it's the co-volume of the lattice you see in the subspace squared, okay? Another way to see this is it's the restriction of the binary form you get on the lattice when you take the quadratic form sum of 4 squares and you restrict it to the lattice, okay? That's also why it's an integer, for instance. Good. So given this discriminant, we can collect all rational planes with the same discriminant in a set, okay? And one can actually show that this is a finite set. That's not too hard. It's non-empty if and only if the discriminant satisfies this congruence condition here. Okay. This is essentially due to Coe and Mordell, but can be proven using our methods as well, which are rather elementary. Okay. In this case. Okay. So, and if it's non-empty, you can show that the discriminant has the set RD of rational planes of discriminant D has this size. Okay. That's yeah. I should say it's a consequence of Siegel's lower bound. Okay. But let me not make this more precise than what I just said. Okay. Good. So right. So we have this set RD. Okay. And as I said before, our goal is to associate to any such plane in the set 4 CM points. Okay, so 2 are rather simple to define. So you have this subspace, okay, and we rotate it to a fixed copy of R2. Okay, say R2 times 0, 0, whatever. Okay, and what you get is a lattice in there. Okay, now the so obtained lattice is not well defined per se because you chose a rotation. So what we do is we look at the set of lattices up to isometry, which is this thing. And yeah, so by looking at the lattice in the subspace, we get well-defined point in here, okay? And if you want to draw a picture of that, it's the same thing as taking the complex modular curve, okay? And identifying with the reflection around the y-axis, okay? So it's essentially a half of the complex modular curve, if you want, okay? Right. So now the problem is in some sense symmetric, okay? So if you have the subspace L, then your Fognon complement is of course also a two-dimensional rational subspace, and actually of the same discriminant, okay? And we can define in the exact same fashion the shape or, yeah, CM point attached to the Fognon complement, okay? So we have 2 CM points, and so, okay, these are rather directly defined. The second 2 use a very nice quaternionic trick that I would like to explain in detail, okay? And what the quaternionic trick does, in a nutshell, so it identifies this Grossmannian, okay, of two-dimensional subspace in R4 with a product of 2 spheres. Now, it does that in a nice fashion, okay? So if you take a rational subspace, the line through the 2 vectors that you see, okay, these lines are also rational, yeah? would be completely clear from the formulas, yeah. Okay, so what we want to do is we start and we identify our R4 with the algebra of Hamiltonian quaternions, okay, which gives us additional structure. Now, yeah, let me just recall, so it's the algebra generated by three symbols I, J, K with these relations here, okay. And given that, you can define a conjugation, okay, just reversing the sign, a norm, okay, and notice that it's exactly the quadratic form we were looking at earlier, and a trace, okay. It's just some formulas. So, okay, right. Good. Now, yeah, let me restrict to RD and let me tell you how the thing works that I promised. So, okay, so we take some rational plane of discriminant D, okay, and we fix a basis of the integer lattice inside that plane, okay. So I can view these two basis elements as elements of the quaternion algebra, okay, and form this expression, which is weird at first. So you take V1 and then you multiply with the conjugate of V2, okay. Now, okay, and then we just subtract the trace, okay, so we get a vector in 3 dimensions, okay, traceless vector, okay. Now, notice that the trace that we had before, right, was divisible by 2. So since we started off with an integer vectors here, okay, this would be an integer vector, okay. Good. And we define a second vector in this exact same fashion. And it's not a boring one, it's not the same one, because of course, the Hamiltonian quaternions are not commutative, okay? Good. Right, so we have encoded, essentially, we have given for any such L, we have given 2 vectors, okay? They don't depend on the choice of basis, essentially, because if you look at the right-hand side here, okay, this is an alternating bilinear form, okay? So if you change the basis, you possibly switch the sign in both of them at the same time, but that's all you do, okay? Good. So we have a very natural thing, and actually you can, given 2 vectors, you can get your plane back by this formula, okay? We won't use this formula later on, but just it's a fun fact, okay? Good, so, right, and so the second 2 shapes are easy to define. So we take the first vector, okay, of L. We take the following complement inside the traceless quaternions, okay? That's again a rational 2-dimensional subspace, and we take the shape of the lattice inside that, and the other, and well, we can also do the same thing for the second vector. Okay, so we have 4 points attached to L, right? So this one, and these 2 here. And so here's the theorem, okay? If you take, so we fix 2 out primes, and we look at the tuples where, again, yeah, we attach to L all its 4 CM points, okay? So it's a large tuple. And so when the discriminant goes to infinity, okay, along the, well, non-boring sets, and satisfies this weird condition, so minus D should be a non-zero square modulo both primes P and Q, okay? Then the tuples are actually equidistributed, okay? Inside this huge space, okay? Yeah, good. Okay, so let me first note that the P and Q here are completely arbitrary, right? So it's a weird condition, okay? To assume this is an artifact of the proof rather than something you should see as necessary for the theorem. And in fact, we can show that if you do the same theorem on average, meaning that you look at all L up to discriminant D, okay, then the theorem is true without these 2 primes, okay? Now, yeah, this average version actually implies previous work by Maas and Schmidt, okay, who look at subspaces and the shape of the lattice inside the subspace. No, I don't. No, I don't. So the condition should not be necessary, but it's very much important in the proof. Okay. So what the condition does, it assures that actually that we have a high rank diagonalizable action. Okay. So it's, in fact, you should see it as a splitting condition of a certain torus. I will introduce it later. And so yeah, we cannot do without it in the proof because it's a, well, okay, because it's a non-effective proof. That's another reason for it, yeah. Okay. Right. So if you stare at the individual factors, okay, it's a joint equidistribution statement. If you stare at the individual factors, say just L, then the equidistribution follows from Duke's theorem, okay? And since truthful, to be completely honest, what you see in here, okay, is not the full set of CM points, so ignore what this means. But it follows some refinements of Duke's theorem, in this case from a theorem by Harcos and Michel, okay? So that's in the equidistribution of the individual factors. So, right. So let me say something about the proof. So the group in the background is SU2 squared, okay? So SU2 is just norm 1 quaternions. And SU2 squared acts on the quaternion algebra by multiplying with one element from the left and the other one from the right, okay? And it's trivial to check that this is actually norm-preserving. So what you get, in other words, is a map from SU2 squared to SO4, okay? Which is an isogeny. Right. So, and the map we defined down here, we defined previously, is equivariant for that action, okay? And, okay, so it's not, well, it's not too surprising because that's the way we cooked it up. So what you do is if you apply, say, G1, G2 to L, okay? And then you compute A1 of that, that's the same thing as conjugating A1 of L, okay? And the same thing holds for A2. Okay, good. So the map associating the points, what we call Klein map earlier, has a nice behavior with respect to the section. Now, the dynamics that we look at is actually the dynamics of the stabilizer, okay? So it's the set of guys preserving L, okay? And we take as a risky connected component for reasons you can ignore. So what this is essentially, so it's the group, so you have L and you have the phonal complement of L. It's a group that consists of rotations in L and in your phonal complement, okay? So it's, as a group, you should think of it as SO2 times SO2, okay? And yeah, and what you get by this equivariance formula is that it's actually the stabilizer of one vector times the stabilizer of the other vector, okay? So, okay. So this is the kind of group we want to look at, and right, so I'll be rather sketchy here. What you can do is you can embed this HL in a large product of forms of SL2, okay? How do you do that? So you have, okay, trivially it's embedded in SU2 squared. So you can let the group HL act on L itself, okay? You present that in some basis, and then you get the map to SL2, okay? And we do the same thing for all the other factors, okay? So HL sits somewhat diagonally in this huge product, okay? I will show you an explicit example later on, okay? Now, it's by now, I think, sort of rather standard trickery to see that you can, that the dynamical version that you want to prove of this theorem over here, right, considers equidistribution of what is also called the total packet, like this, okay? Now, so I'm a bit cheating here, so actually you need to project this set onto a quotient, but let's ignore that. Now, okay, so we know equidistribution of these packets, okay, when you project any single factor, okay? That's basically the results I was mentioning over here, okay? So what this says is that if you take a sequence of subspaces L and you look at the weak star limit, the weak star limit is going to be adjoining, okay? And so we can apply the joinings classification and find the Lindenstrasse that I mentioned earlier. And what we need to do is, again, I'm cheating, but what you need to do is you need to rule out that HL is contained in any subgroup that would look like a joining for G, okay? So it's any subgroup that, algebraic subgroup that would project onto each factor of G, okay? And actually, yeah, you need to rule this out in every pair of factors. But yeah, let me make this precise. So, well, not too precise. Let me give you an explicit example of such a stabilizer subgroup, okay? And which would then serve as a reason for you to believe me that what's written here cannot happen, okay? Good. So, okay, let me cheat. So we assume that we want to work with the algebra of 2x2 matrices instead, okay? Which is a completely reasonable thing to do because the dynamics we work with is p-adic dynamics, okay? And over any odd prime, the quaternion algebra we were looking at earlier is the same thing as the 2x2 matrices, okay? And SU2 is just SL2 in this case, okay? We have the same thing. And let's look explicitly at this subspace, okay? So it's a subspace of diagonal matrices. Now it's a quick calculation. If you look at the bases consisting of a 1, 0, 0, 0 and 0, 0, 0, 1, okay? The vectors that you attach to it, this, again, it's just this formula here, okay? The conjugation is the adjunct, okay? The trace is the trace, and the determinant is the determinant. So it's rather simple to calculate, luckily. And what you get is this, okay? Now, okay. So it tells you how you compute this, how you can compute this stabilizer. Oops, no, sorry. Here we are. So it tells you how to compute the stabilizer HL, okay? And what you get is just twice the diagonal subgroup, okay? And for here I just used the equivariance properties that we stated earlier, okay? Now, so what we want to understand is the way in which this product acts on the subspace, the orthogonal complement of the subspace, and the orthogonal complements of the vectors we attach to it, okay? That's the way, that's what we need to understand. Now, okay. So, right. So let's take L and let's understand how A times A acts on L. So if you look at just this basis like we did before, okay? And the product, AS, AT, if you represent that, what you get is this, okay? ST inverse, okay? And in the same fashion, when you act on the orthogonal complement, which is just the subspace of anti-diagonal matrices, okay? What you get is ST, okay? Okay, now remember that if you want to see the way that this guy acts on the orthogonal complement of A1, you need to conjugate by AS, okay? And what you get is AS squared, okay? And AT squared. So, okay, so you get this huge subgroup of SL2R, okay? To the 6, okay? And I put it over here again. And, right. And so for the joinings classification, what we need to see is that there is that for no pair of these, I can find an algebraic subgroup that projects onto and that contains the diagonal group, okay? So explicitly, let's take for instance, the fourth and the fifth, or whatever. So you get AST, AS squared, right, like this, right? And if you had a subgroup M that would project onto each component that comes from a joining, okay? What it would need to do is it would need to, it would either be, okay, essentially it would either be SL2R squared, or it would be a graph of an isomorphism of SL2R, okay? Now, but if you see that, if you look at this, okay, you can vary here each component without varying the other, okay? Say for instance, here you can vary the left factor by varying t, and here, if you take, say, S equals t inverse, you can vary the right factor without varying the left factor, okay? So, in other words, yeah, the only such subgroup can be SL2R squared, okay? And yeah, that's the reason why you should believe the theorem. It's not the proof, but yeah, okay. Yeah, so maybe I stop here. Thank you.